right, da, da, da. Good morning, or just morning for some.
I disagree.
All right. Let's see, we are on, let's see if this makes sense, 4 point, I just want to show you one more thing of 4.3, I guess, and then we'll go from there. So 4.3. You guys tell me what example we're on, and we'll go from there.
We were on Windows 7.
So now we're on example 8.
You were like basically right. You just didn't.
Yeah.
You didn't finish your.
I just don't.
You were like
You were totally right. I just thought I would
just-
clarify slightly.
You were like pretty much right, but you weren't.
You were 100% correct. You just didn't finish the statement.
You were entirely correct, except.
4.3. I think we're done there. That's good enough. I think I can actually say it in the next one. So 4.3, just talk to me. We are done. 4.3, right?
You said we
weren't quite done.
we weren't
Not
done,
quite done.
or whatever.
Let's play the basics.
All right.
Probably not.
I guess so. Okay, almost done. How about that?
Sounds good.
Almost done. Before we get there though, let's jump to. I want to see if I can jump out of here. That's what I want to do. Screen, show, taskbar. I forgot to print these out for you, but at least want to talk to them so I can email it to you guys here. So let's go with it. Da, 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 da. I got some challenge problems here for you guys. Oh, what? Oh yeah, awesome, Mr. Najib. Thanks for the challenge. No? There you go.
Yeah.
I need more time.
It's not
So here's a few things. We talked about the Ferris wheel the other day, right? Did we talk about the Ferris wheel? Yeah, we did. Huh? Okay, so we have a little challenge problem here. So there are several Ferris wheels in the world today. Anybody know where the biggest one is? Oh, that's right. Hold on. So I got to do this one here for you guys too here. Man, all this fun stuff here. Here's the construction of the world's tallest Ferris wheel. I'm not sure if and I'm not going to show all of it here, but here's could you imagine creating an island
Just to go to Ferris wheel.
to house the Ferris wheel with other shops there too?
I like how we prioritize things. Let's put an island so we can put up there.
Yay!
I
There's
respect.
probably some random billionaire who just wanted to do it because he could.
You know what, of all the
Or the
things
country of
that
Dubai.
I'm not upset.
Yeah, it looks like Dubai.
I'm upset. Can he like cure world hunger?
I know,
it's not charity.
No, Ferris wheel.
No, this is Dubai. You get away to short the other tigers.
We
Yeah.
don't do
Because
that.
that's
People don't have
bad.
it where
They're
they don't deserve to
domesticated
eat
tigers.
unless they can.
Capitalism.
I just think that
I
there's
don't
other
understand
socialism
this window.
about like
So. No, Grant, socialism is one more half.
And there's
Oh, that is a lot of.
go with me. Let's see.
I would not like to be a worker on that.
No fun?
Socialism is one half.
No fun being like right there,
No.
staring down.
With his little hook.
Yeah.
Actually, I did.
Anarchism is one
Okay.
negative icon. Of course.
I like how they have to
You
build
have
an
one,
entire
but what's
structure to
substitute?
build the structure so that
I'm
they
glad
can get
you
around.
agree on
And I think they built it right next to the waterfront because they had to bring in things
Yeah.
because you couldn't do it any other way.
Nice.
And so look at that. How fun is that? That's one. Is it? Yeah, I think that's one of those
Oh my God. I like saving the
the
world.
side, what is it called? Spindle? No, that's not a spoke.
Spoke.
Spoke, there you go. Yeah. There's one spoke.
Whoa.
And then I like the last part here. This last part is they're putting on the they're putting this on, and so it took a crane, and they had to be. It's gonna actually say
People. What about that?
that's what it's supposed to look like right there.
Oh, yeah.
Wait, so they're still building it?
I think they completed it in 2019
No, it's
or 2020. I believe it's done now.
Ah,
You're not even finished.
British people.
Oh my
Rich
God.
peel.
And I love the little disclaimer here. It says that they had to be within the 6 millimeters because it's
Nice.
round, so it had to fuse together.
Great.
Oh.
That's so cool.
I'm okay working on that.
Yeah.
Dropped it.
Can you imagine living in the clay?
That would be literally how
Yeah,
much you drop it on accident.
That would be pretty funny.
Well,
Oops.
I think it's by the left.
Then it's not your fault. And then it's just
No,
funny.
how do you forgot?
Hilarious.
Because something broke.
Like if I set it on top and the whole thing just fell.
There you go. It had to be a 6 millimeter gap.
Just collapsed. Nice.
Oh, I would not want to be one of the workers on the
Yeah,
little thing
no, I
waiting
would
for it.
not either.
Yeah, that is sizable.
All right, and they
Like
did it.
nodding
Da,
their
da,
head.
da. Uh-huh.
I started missing the wheel part, but I hope
Incredibly useful.
All right.
Imagine they just leave it like that, they just run out of thunder.
Really fun, I know.
Yeah.
So that's what it's supposed to look like right there.
Whoa.
Is it not even done?
1400.
Oh my God.
And virtual reality, what it looks like inside. Let's see.
Bro.
Oh, that's cool.
Wait, what? Okay,
Whoa.
And it's supposed to roll with the, because the gravity's on the bottom, right? So it's supposed to roll with the gravity. So it's,
Okay.
you're not gonna flip.
Your regular Ferris wheel.
Yeah, so you have like a whole bathysphere attached to it.
Well,
Yeah, and they're,
I
um,
see why that's why I'm voting
Yeah,
for
that's
something.
really cool.
I admit.
Yeah, this is more important than solving.
whatever. Yeah.
How much does it cost to ride on this?
Do not know. I think they completed construction this year, last month.
Oh my gosh,
Last
we're
year.
just having a meal.
Wait, okay.
I want this. Did they senior trip? Senior trip.
Yeah. Stuck here.
So you got like someone there and stuff.
You can even take some.
Like you can eat your meal right on the Ferris wheel. Why? Why?
Maybe there's a reason why there's only a sheik celebrating his birthday. That's about it.
Oh, yeah.
All right. That was kind of cool. So Ferris wheels. Actually, they're now being called observation wheels.
Oh,
What?
why?
Why?
That's the new nomenclature. I don't know.
My man Ferris. Yeah, what did Ferris do? Really hard to invent the Ferris wheel. He deserves to have a name now.
Yeah.
So we have George Ferris, a long time ago, built the first one. So here it is. Your job assignment is if you
Build a bigger Ferris.
Yes, exactly.
or
That
solve
is-
world hunger. One of the two.
Either one.
I'll probably solve world hunger.
Yeah.
That might be better. Definitely not better, but easier.
What if you
Never
solve
mind,
world
become a
hunger
billionaire.
using the Ferris wheel,
Oh,
yeah.
All right, so here we go. We did this in class, but you guys are supposed to pick a, so real quick here, this is the challenge problems here. So honor students, you guys have to do it. Canon students, yeah, honor students, you have to do at least one, right? I think that's the way we did it. Yeah,
Yeah.
we got to pick one to do at least. Canon students, it's extra credit. Is that the way we did it?
yeah.
Okay, great.
I just remembered from the last that we didn't, you know how you sent out the thing later for that? I included it with my homework, but I never separately included it with the other link you sent out.
Oh, perfect. That's okay.
So, I'm
Yeah,
hoping that
yeah, on some of them,
got it.
yeah. As I started grading them, I noticed that, so.
Okay, good.
Okay, so pick a Ferris wheel or observation wheel. I like Ferris wheel. And figure out the diameter, the height, and how long it takes to make one complete revolution. And can you give me a sine or cosine function that demonstrates that? We good?
No.
Yes. Okay, next. Next is, so far we've been dealing with sine and cosine. So you should notice that sine starts at 0, 0, right? It goes up and down. And cosine starts at 1 and goes up and down. But then really, it still goes up between 1 and -1, right? So since we introduced the whole concept of phase shift, can you somehow relate sine to cosine? And I'll send this out via email here afterwards. Okay, next. The moon.
What's that?
This is us modeling world behavior, or at least moon behavior. So if you go to timeanddate.com and you scroll down under sun and moon category, there's something called moon phases there. So if you click on it, it'll tell you new moon, full moon, and half moons there. Good. And you gotta click it for this year only, right? For 2021. So what you want to do, you're going to create a sine or cosine curve or formula, whichever one you want, and predict the percentage of the moon that's showing. We good? So this one's not gonna go from 1 to -1. It's gonna go from, you guys say?
1 to 355.
Yeah, 100%. Full moon, right? 0 new moon, right? So there's that fluctuation. So you have 0 to 100. And then the day we're going to take the chapter 4 exam, the night before, you do have to look up in the sky to see if you're relatively correct. Like, but that's about 35%. That's cool. We good? I think that's a cool one. I like that one. Okay, and last one. Da-da-da. The temperature chart. Those of you have worked with Desmos, raise your hand. Have you guys worked with Desmos on that? Okay. How many like Desmos? All right, that's cool. Okay, so given the temperature, this is not going to be perfect exactly-ish, okay? This is going to be kind of close. So this is high temperatures that closely model S low. So on an annual basis, usually temperatures go down and up. So can you plot a Desmos graph that is pretty close to the dots that you've made on that? So how do you make a dot in Desmos? Anybody know? The only thing is, I think you're going to be, I guess you're going to be off a little bit here, because if you want to designate this as 1, then you go 164. So in Desmos, do we need to go there or no? You guys okay? Can you Google it? So you have to put in the dots first, right? So at Desmos, you just put it in the chart, you put 1,64 in parentheses, you click on it, it'll give you a little dot in Desmos, right? You got to figure out how to do your X and Y domain and range things, right? So it fits in nicely, and then go for it. And then you print out or do a screenshot of it, send it my way, or print it out and complete with the assignment, whatever you like. We're good? So there it is. I will email this to you guys today sometime. We good? But there's your 4 challenge problems, which I think that'd be kind of cool. Okay. Zoom back to here. And where are we at here? Okay. I think we're ready now. Go here. 4.4 for graphs here. 4.3 we did. That was I'm just thinking if I want to show you the way the book does it, so a different way to do it. I guess we should. Let's do that here. So we're not almost done. We're almost done. Not almost done. Almost done. 4.3. Want to show you the way the book does it. I guess it's useful to know. We are an example again. 7? 8. Thank you. Graph, and we're going to do some graphing here. All right, I think this is the one we left off on, right? Is that true? Is that something, did we graph something like this? If you look at example number 7.
Yes.
I think it's the same exact one, is that right? Okay, so example 7, that was the way I like to do it. Example 8 is the way the book, I should put the book method here. How about that book? The book method, that's what we're gonna study. Cool. So especially if you want to just graph one complete revolution, Let's go with it. So let's go back over here. If you do one complete revolution for sine, everybody agreed here? Sine goes from 0 to 2 pi, agreed there? So what we do is we take this little middle section right here, and we are just going to substitute that little middle section inside for our one complete revolution. Are we good? And so I should introduce it. So example 7 and 8, the difference between them really is in example 7, if you have a very clearly defined domain structure you got to work with, usually example 7 is the best, because then you're like, okay, that's the period, that's the phase shift, that's it. If you are planning to just do one complete revolution, doesn't matter where it is on the graph, this is probably the better one, because then you just put it together.
Even though the period would only be to pi, the revolution is always 2 pi?
No. So this is a little different here. So this is the normal period right here.
Okay.
So one complete revolution is what I want you guys to do. That's these two a little separate from each other here. So the normal period for sine is that one right there. And then what we're going to do is we're going to work with it to give us that right there. So do you guys remember doing this in algebra? Something about maybe like clearing the denominators first. We're just going to multiply everything by 2 everywhere. So that becomes 0. Let's see, that becomes 4x. That becomes, hey, that's just minus 3 pi. That becomes 4 pi. Everybody okay there so far? I think we did these in algebra, and then algebra 1 as well. Talk to me. Raise your hand if you remember this. Cool, okay. Adding 3 pi to both sides. Guess that's what we're going to do. To cancel off the little middles here. So I got a 3 pi in this way. I have a 7 pi over here. Divide by 4, divide by 4, divide by 4, and voila, I have cool. Okay, so for one complete revolution, I got it. I got exactly what I need to do here. I am going to go from 3 pi over 4, which is all the way over here. And I need to end this all the way at 7 pi over 4. That will give me one complete revolution. So that's how much the phase shift has moved. Now the question is, can I divide it into 4 pieces? In this case, I think it's pretty good because you got 3 pi over 4, right? If you divide it in 4 pieces, it would be 4 pi over 4, 5 pi over 4, 6 pi over 4, and 7 pi over 4 would be the last piece. So this one would be 4 pi over 4, which is just pi. 5 pi over 4. 6 pi over 4? What is 6 pi over 4? It's going to be 3 pi over 2. Talk to me. Does that make sense there? Cool. And so notice now, I really don't need to, remember how last time on Monday we shifted each of the dots over, right, each time? And then we have to imaginary sort of go backwards a little bit here. So, oh, that dot would have been here, and then we move it forward.
So
this time.
Is 3 pi over 4 like the first unit of that, or is there more in front of it?
That is the first unit. We could put in 2 pi over 4. If we wanted to, we could put 2 pi over 4, pi over 4, and that gets us back to 0 if we like, if we want to include all the units here. But there it is. Look at that. The sine curve does not change. It's going to stay exactly the same. We just need to make sure that we go up to 4, down to -4. But look at this little sine. 3 pi over 4 is a starting point. And remember, sine goes like this, or it goes up and down. That's cool. So there's that dot. That dot is all the way up on top, back to 0, down to -4, back to 0, and voila. There is our curve. And real quick here, can you go back, look at example 7, and talk to me? Is that what we got as well?
Yes.
I think so, yeah.
Is that re-up?
Where?
Okay.
Good there? Okay, I want you guys to try 1 as well. Let me try an easier one here. See a few people still finishing up here. Go for it. Tell me if you need more time. Good, good. Example 9, all yours. Graph for me. I think this one be. All right, one complete revolution of this right here. All yours. Give you a minute. Try it yourself here.
Why did you start off multiplying by 2 in example 8? Was that from the 2 pi or the 2x?
It was because of the
wait,
the denominator of 2.
Denominator of 3 pi over 2.
Yeah, that makes sense.
All right, let me start it as well. So again, we're going to take this little piece here and we're going to say cosine has a 1 revolution is completed from between 0 and 2 pi. And let's work with this here. Clear our denominators first. Get rid of the 2. This little guy right here, that little 2. We want to get rid of that one. So if there were no fractions, we would not be multiplying by 2. So 0 times 2. Okay, this is going to be 2 times through, which is 6x minus, ooh, this is fun. Let's see, 2 times pi over 2 is going to be pi. Now I got myself a 4 pi. Grant, doing okay?
Yeah.
Cool. Adding pi to all 3 sides. That's cool. Grant, you have a new way to study. It's called study by osmosis. Right? Just let it in. All right. Sounds good. This is what, 5 pi? Yep, 5 pi. So divide by 6. Oh man, this is going to be interesting. We have a denominator of 6 here. So 1 complete revolution for cosine is going to happen between pi over 6 and 5 pi over 6. So think of that's very, very small, isn't it? Between, if you think about just, if you think about between 0 and 2 pi, we are like right here and up to here. We're going to do all of cosine in this little piece right there. So let's go for it here. So cosine is, starts high, right? It goes down and comes back up to high. There's my cosine of x. Cool. So pi over 6 is here. So 2 pi over 6, 3 pi over 6, 4 pi over 6, 5. I like it because then everything is in terms of just pi over 6. So notice you don't do the x scale until you know what this is, right? Okay, so this is pi over 6. This is 2 pi over 6, which is, I think it's pi over 3. Then we have 3 pi over 6. Anybody? 3 pi over 6? Pi over 2. 4 pi over 6. 3. Okay, and there. I think that's cool. That's a good scale from it here. And we are ready. We're going to go up to 3, down to -3. So we got this guy here. Cosine goes down here. Here's my critical points for cosine. Down, and then back up. Okay. So that means if it actually did go still back to the 0 marker, where would the 0 marker be? You're going back to x equals 0. Where would the line be at x equals 0? Again? At the origin. That's cool. It would have been right here, which actually would make it look just like a sine curve, huh? Wouldn't it? That'd just be a sine curve from 0 to 2 pi over 3. That's weird. And that all looks the same. Okay. Boom, boom, boom. Okay, talk to me. Are you guys comfortable doing the graphs at least? Let's go with it here. Example 7 and 8. Anybody like the way we did it earlier? Example 7, was that easier? Because you just list everything on the side. You list amplitude, period, phase shift. And then you just kind of plot it, or this way is a little bit better. What do you guys say?
I think 7 felt like it made a little bit more sense to me, like quicker, but I think
It's an eh.
they're just different. They just feel like, like
Yeah, they are just two different ways to do it. So, and I don't think any one of them is faster either. It's just this one. Okay. All right. Nobody else knows thoughts. Okay. Sounds good. Let's go with it here. I did want to do a couple of things here. So, example 7. Exercise 10. Different one. Let's go with it here. So here's what we have. We have a little platform here, and we have a little coil coming all the way down. And then we have a weight of some sorts. Good there? And then the next thing is we're going to take the coil. We're going to pull this little weight down to about right here. And so we're just going to let it go. It goes up, it goes down. We're good. Goes up and down.
Oh no.
Oh, no.
Started again. Where is it?
God, this is infuriating.
Oh, he got it all the way behind the school.
Oh
I
wow.
see his head coming back down.
How far? The street doesn't even.
I don't know. I saw him all the way at the end of the fence.
Drug dealing every time it goes on. No alarm. Oh no, my backpack. I'll be back.
Yeah, no, that's his plug's ringtone.
Yeah.
All right, I'm gonna go with this one here. Here's your formula of what happens. So the length of the coil is given by that right there. And so we pull down the coil, let it go, and it just wobbles back and forth. And these guys are called harmonic motion or oscillating motion.
I'm sorry, I just tried to shield my eyes from the sun to see better inside the comments. Doing well.
Wait, he went back. What? You see that?
No, I can't.
He was like back over there, and then now he's back.
The poor neighbors are like, what is this ringing in my ear all this time?
Never found it.
Okay, the neighbors are obnoxious, they should be annoyed.
The neighbors definitely sell drugs.
Yeah, I know. We think you are drug dealing each time you go out.
Or
I don't know nothing about that.
I saw the shoes on the wire.
I don't know anything about that, Grant.
I'm pretty sure that's just your plug's ringtone.
I'm so curious as to what the noise is.
Yeah, I found a little zipper area I hadn't noticed before, but anything didn't seem to be behind it, so.
Oh,
I don't
no.
know. It probably doesn't have like secret compartments or something.
What is the final one say?
Sketch from 0 to 5.
Yeah, that's true. I just really need to get it.
Does first thing say short?
Yeah,
Yeah, I mean, my dad goes behind my back and does things so frequently that I wouldn't be surprised if he was like outfitting the whole.
All yours. Try to see if you can find the longest length of the coil, and then the equilibrium point. And then can sketch it from 0 to 5. So it looks like 0 to 5 seconds. That's the way we go about it. So try it yourself first. Bless you. All right, those waiting for me, let's go for it here. So we've been kind of looking at this here before here. What's the highest cosine could ever be?
1.
1, right? Lowest it could be? -1. So in this case, really, 1 is the highest, -1 is the lowest. For this little piece right here, it doesn't matter what the period is, right? It doesn't matter what the phase shift is, because that only scoots things sideways, right? And it only makes it go faster on the inside, but it doesn't affect the minimum, maximum values of this. So if we were to put this in, the maximum for cosine is 1, but when we put into this little equation, that might not be the maximum value of the equation. We good? Because you could be subtracting things instead of adding things. So then on the bottom here, -1 is the other part. So this would be 15 minus 3.5 times -1.
Wait, can you explain what you just did there? I'm sorry.
Sure. We talked about cosine being the highest cosine will ever go is 1 if it's just cosine by itself. The lowest it'll go is -1. So I just kind of did both of these here.
Plug
One,
those in for each one and -1.
and plug those into the equation itself. So just because cosine has a maximum of 1 doesn't mean the value itself is going to be the maximum of the equation. Cool. All right. So it looks like 15 minus 3.5. What do you guys say? 3.5 times 1 will be 3.5. Subtract that from 15. I think I heard 11.5. Is that right? Okay. And then this one's going to be 15 plus 3.5. 18.5 is perfect here. So that means the shortest length here would be 11.5. And we are in centimeters. cm. The longest side would be 18.5 cm. Okay, we good there between those two? That's cool. And I like the fact that it actually switched the the maximum and the minimum. That's the important part there. Okay, equilibrium point. How long is the coil sitting if we're not moving it? It goes just right in the middle. How would we find that one?
Just whatever is in the middle of 11.5 and 18.5.
Sure, yeah, right, because it oscillates between the two, therefore the middle is going to be that right there. Talk to me, what would that be? 15. And two ways, right? Grace says figure out the middle between 11.5 and 18.5. You add them up, I believe. Divide by 2, that would be the middle, so that's how we get the midpoint. Or we just look at the 15 here, right? Because cosine fluctuates between -1 and 1 at 0, right? So if you want to lift this up or lift it down, it's going to be that value over there. Cool, okay, let's sketch this now that we got this. Take care of all yours to sketch. Give you a minute here, try it yourself. Can you sketch this? And I need it from 0 to 5 seconds. All right, I'm going to start it as well then. Let's see. I guess we could do just simple here. So we're looking at a cosine curve. And do we have a phase shift on our hands? Is it scooted sideways any? It isn't, huh? Because there's nothing, we have the 2 pi t, right? But then we don't have any adding or subtracting afterwards, right? So that's nice. It's gonna work just like a cosine curve. So in my mind, cosine works like this, right? So we have on our hands is, let's see, amplitude is a 3.5. We're good. It's the absolute value of, let me go like this here. It's the absolute value of the number right in front of cosine. Period. It's going to be 2 pi divided by, what do you know? Is it true? 2 pi divided by 2 pi? I go with that.
Wait, can you explain that?
Sure. It's this little piece right here. So it's the C value. So let's see, it's going to be 2 pi divided by, and that was the B value for us before. The B value is whatever is the little multiplier to our variable. In this case, it's that. again, the power of radian measurement. We get to go to real numbers over real numbers here. I think we're good. So now all we have is we have a vertical shift of 15. And then we do have a reflection. There you go. That's what I was missing. Reflection, yes, because of the negative in front of the 3.5. And are you guys all done? So I'm gonna go like this. So I'm gonna go all the way, this began my 15, 16, 17, 18, 19, 20. So about there, that's gonna be 10. That's gonna be 5, so that's 5, 10, 15, 20. I'm gonna go in terms of 5. The 10 should be a little bit higher. Probably about right there. Okay, and then 5 goes here. So we have 4, 3, 2, 1. This is in terms of seconds. And so we have our starting point, 11.5, about right there. Tell me if you guys agree. Because we have ourselves an upside down cosine curve, it's going to go like this now, right? Because of the negative, it's going to go to 3.5 to negative 3.5 because of the amplitude, and then it gets shifted up 15 units. So the middle point is now here. Are we good with that one? Cool. So 11.5 is right there. Ooh, that's fun. How long does it take to do one complete cycle? What's our period? Just one. So in this case, if we break this up into 4 pieces here, it goes here. It goes here, up to 18.5, back to here, back to this little piece by 1, which kind of makes sense.
10 times bigger.
So final answer, here it is. How about it goes like this, comes back down by the time we get to 1, it goes up again. There's 2, 3, 4, and 5. Are we good? It's going to go 5 times 5 periods by the time it hits 5 seconds. Yeah, and we've modeled it. Da, 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 da. Go from there. Okay. I think we're good. And we're good for the day. And we're finally done with 4.3. Officially.